मैं आनंद कुमार खत्री। आज के हमारे लेक्चर का विषय है बायोस्फीयर पार्ट 3। द नाइट्रोजन साइकिल। नाइट्रोजन is one of the elements most likely to be limiting to plant growth. Like carbon, nitrogen has its own biogeochemical cycle, circulating through the atmosphere, lithosphere, and hydrosphere. Unlike carbon, which is stored primarily in sedimentary rocks, most nitrogen occurs in the atmosphere as an inorganic compound N. It is the predominant atmospheric gas, making up about 79% of the volume of the atmosphere. Plants, however, cannot use nitrogen in its gaseous form and are able to assimilate it only after it has been converted to ammonia NH3 and nitrates NO. This reductive process, called nitrogen fixation, is a chemical reaction in which electrons are picked up from another molecules. A small amount of nitrogen is fixed by lightning, and most of the nitrogen harvested from the atmosphere is removed by nitrogen fixing bacteria and cyanobacteria, formerly called blue-green algae. This is the diagrammatic presentation. The nitrogen cycle transforms the nitrogen gas. Certain species of nitrogen fixing bacteria can coexist immediately symbiotically with legumes and other plants, providing the plants with necessary nitrogen. In this symbiotic association, the bacteria become encased in nodules that grow on the roots of plants, through which nitrogen that has been fixed by the resident bacteria is obtained. Cyanobacteria have developed similarly relationships with various life forms, such as liverworts, hornworts, cycads, and at least one genus of flowering plants, Gunnera. Their symbiotic relationship with the fungi has earned its own designations. The coexistent species are called lichen. This is the diagrammatic presentation, the roots of the winter pea plant. Other microorganisms perform important tasks that propel the nitrogen cycle along. Although plants can assimilate ammonia as well as nitrates, most of the ammonia in the soil is converted to nitrates and then to nitrates by certain anaerobic bacteria through the oxidative process of nitrification. Once nitrogen has been assimilated by plants, it can be converted to organic forms such as ammonia, acids, and protein. Animals can use only organic nitrogen, which they obtain by consuming plants or other animals. As these organisms die, certain microbes such as denitrifying are able to participate in the decomposition of organic nitrogen into ammonia. Ammonification providing a constant supply of ammonia to be used in the process of nitrification. Although the fixation of atmospheric nitrogen is an essential part of the nitrogen cycle, ammonification and nitrification are the predominant methods by which organic nitrogen is prevented from returning to the atmosphere and is kept cycling through the biosphere. Some nitrogen does not return to the atmosphere, however, as denitrifying bacteria break down nitrates to obtain oxygen, thereby releasing gaseous nitrogen. Nitrogen is also lost from plants and soil in terrestrial environment via other routes, including erosion, runoff, volatilization of ammonia into the atmosphere, and leaching from soils and lakes and streams. Eventually, some of these nutrients reach the ocean as rivers flush them onto the ocean surface. The sulfur cycle. Sulfur is found in all living organisms as a constituent of some proteins, vitamins, and hormones like carbon and nitrogen. Sulfur cycle between the atmosphere, lithosphere, and hydrosphere. But unlike these two other elements, it has major reservoir in both the atmosphere and the lithosphere, as is true in the nitrogen cycle. The activities of the microorganisms are crucial in the global cycling of this nutrient. The process begins with geochemical and meteorologic processes such as the weathering of rocks. When sulfur is released from the rock and comes in contact with air, it is converted into sulfate SO4, which is taken up by the plants and microorganisms and converted into organic compound. Animals acquire these organic forms of sulfur and from their foods. When organism die and decomposes, some of the sulfur enters the tissue of microorganisms and some is released again as sulfate. There is, however, a continual loss of sulfur from terrestrial ecosystem as some of it drains into lakes and streams and eventually into the ocean as runoff. Additional sulfur enters the ocean through fallout from the atmosphere. Once in the ocean, some of the sulfur cycles through marine communities as it moves through food chains. Some re-enters the atmosphere and some is lost to the ocean depths as it's combined with iron to form ferrous sulfide FeS, which is responsible for the black color of the marine sediments. Sulfur re-enters the atmosphere naturally in three major ways. Sea spray releases large amount of the elements from the ocean into the atmosphere. Anaerobic respiration of sulfate reducing bacteria causes the release of hydrogen sulfide gas, especially from marshes, tidal flats, and similar environments in which anaerobic microorganisms thrive, and volcanic activities releases additional but much smaller amounts of sulfur gas into the atmosphere. Since the Industrial Revolution, human activities have contributed significantly to the movement of sulfur from the lithosphere to the atmosphere, as the burning of fossil fuels and the processing of metals have occasioned large emission of sulfur dioxide. Oxides of sulfur and nitrogen contribute to the acid rain that is common downwind from these industrial activities. The cycling of phosphorus and other essential nutrients. Most other major nutrients such as phosphorus, potassium, magnesium, iron, and calcium enter terrestrial communities through the weathering of bedrock. These nutrients lack a volatile gaseous state. Consequently, they cycle through the biosphere differently from carbon, nitrogen, and sulfur, all of which sometimes occurs as volatile gases. Of the non-volatile nutrients, phosphorus is the one that most often limits plant growth, especially in aquatic environment. Phosphorus and the other non-volatile elements move unidirectionally from land through aquatic environments into ocean sediment. Most phosphorus cycling occurs between the surface and depths of the ocean. When near the surface, phosphorus is taken up by the planktons and passed through the food chain. It cycles back to the ocean bottom as individuals die and fall to the ocean floors, releasing assimilated phosphorus. Much of this element gradually accumulates in the ocean sediment as particulate phosphorus and is eventually brought back to the surface only through ocean upwelling and tectonic activities. The ocean sediments are therefore by far the greatest reservoir of phosphorus. In terrestrial ecosystem, much of the available phosphorus moves in a closed cycle between living organisms and the inorganic debris in the soil. Phosphate is the only important inorganic form involved in this cycle. Microorganisms in the soil break down litter and other organic matter, thereby releasing phosphates, which is then taken up by the plants and released again when they die and decompose. Soils differ in the amount of phosphorus they contain, and in some phosphorus poor soils, almost all the available phosphorus resides in living organisms and organic debris. In some tropical forests, such as those in parts of the Brazil, so much of the phosphorus is contained in living organisms that the clearing of forest eliminates most of this element. As a result, the plant communities cannot recover and crops cannot be grown. The addition of phosphorus to soil poor in this nutrient and the use of phosphorus-rich detergent have had a great impact on the phosphorus cycle in many ecosystems. Runoff from agriculture feed and the emptying the sewage has introduced so much extra phosphorus to river and lakes that population of plants and microorganisms has grown explosively, sometimes creating a solid mat that extends over the surface of the water. This growth increases the amount of organic debris in the water, which can lead to a decrease in the available oxygen, resulting in suffocation of fishes and other animals. The hydrologic cycle. A portion of the biogeochemical cycle of all elements involves time is spent cycling through the hydrosphere. Water itself cycles within the biosphere. Unlike the cycles of the other major nutrients, however, the hydrologic or water cycle would continue in some form even in the absence of living organisms. Most of the earth water is in its core, in its sedimentary rocks, near its surface, and in the ocean. A minute percentage of the water, however, continually cycles through the atmosphere, ocean, terrestrial environment, mainly by the processes of evaporation and precipitation. This part of the hydrologic cycle is driven by solar energy. Water evaporates from both the aquatic and terrestrial environment as it is heated by the sun's energy. The rates of evaporation and precipitation depends on the solar energy, as do the patterns of circulation of moisture in the air and currents in the ocean. Evaporation exceeds precipitations over the ocean, and this water vapor is transformed by the wind over land, where it returns to the land through precipitation. The water falling onto terrestrial environment seeps into the ground or runs off into lakes and streams and eventually empties into the ocean, carrying with it many of the other major nutrients. Water also re-enters into the atmosphere through the evaporative loss of water by plants transpiration. Links among the cycles. Although the overall patterns of the cycling of all the major elements is now known, there is still much of to learn about the relative importance of the different stages of each cycle. For example, there is a considerable debate concerning which ecosystem act as the major source of carbon for the atmosphere and which act as sinks by the accumulating more carbon than they release. The ways in which the different cycles interact with one another also must be minutely studied. It has been discovered that sulfur availability influences the rate of nitrogen accumulation in plants, and nitrogen availability influence phosphorus uptake. All three elements are through, though, to influence the rate of carbon accumulation by plants. As a result, changes in any one of these nutrient cycles influence the other cycle as well. The fact that disruptions in these cycles may have within the biosphere are not clearly understood. Natural geologic phenomena such as ice ages and major periods of volcanic activities have repeatedly distributed these cycles throughout Earth history. Many human activities may have impact of similar scopes. Deforestation, the burning of fossil fuels, and increased fertilization are disturbing these cycles. These anthropogenic disturbances have increased atmospheric level of carbon dioxide and decreased ozone level and undermine the natural equilibrium of streams and lakes by excessive nutrient enrichment from sewage, fertilization, and factory waste, cultural eutrophication. Gleaning more information about the biogeochemical cycle and their interaction has become increasingly important now that the effects of human activities are becoming more apparent. Another potential effect that may result from human intrusion in the atmosphere environment is global warming. Carbon dioxide in the atmosphere has the ability to act as an insulator, preventing some of the Earth's heat absorbing from solar radiation from escaping back into space. This process, known as the greenhouse effect, and is suspected of being enhanced by a rising level of atmospheric carbon dioxide, which have resulted in part from the combustion of fossil fuel and the clearing and burning of tropical forests. This increase in atmospheric carbon dioxide and other so-called greenhouse gases could raise the overall global temperature, causing the polar ice caps to melt, sea levels to rise, and the Earth's precipitation to be redistributed. The complexity and the interconnectedness of each of the biogeochemical cycles make it difficult to pinpoint how any one human activity is altering the cycles. Nevertheless, the majority of those who study these fluctuations agree that this is happening. Disagreements generally concern the extent to which various activity affect particular cycles and what the long-term consequences of these disturbances will be. Thanks.